with you. Thetha mama kaloku. Ubona ngobana useklasini. Elo mntana ohlala khona uTrisha.
Right. Afternoon, everybody. Remember, this lesson is going to be recorded and then it will be available on YouTube if you want to download it. Today's lesson, we're going to do forces. We already did forces in Q1. So today and tomorrow, we're going to spend on that. And then next week, we're going to start with electricity and electrostatics. That's the planning that we have. Remember, tomorrow's lesson will start at 9 o'clock. So the science is a bit different from the maths. The maths is every day at the same time, but the science for tomorrow is going to start at 9 o'clock. Okay. Right. Okay, ek kan nie record. Is hy klaar besig? Okay, so let's start with the lesson. All right. First thing is, there I just made a summary of the type of forces that you can expect to have. So that's a type of force. What is a normal force? What is weight or gravitation force? And here I just want to remind you that the symbol, normally the symbol that we use for weight is a W, but you can use F gravitation because it's the same thing. Weight and gravitation force is going to be the same thing. Then we have applied force. Friction force, small letter F, as you can see it there. And then the next one is, of course, the tension force. Remember, when there's a rope attached or a wire or anything like that, then it's a tension force. Although it can be, you can see it as an applied force, but when we have a rope, they say the force exerted by a rope or a wire, where the rope or the wire is kept tight by the force at both ends, the force is equal at both ends. And therefore we call it a tension force. So there's no place in a rope between two objects where the force is going to be stronger at the one side and weaker at the other side. The force is going to be the same for the whole rope. Okay, right. Now, in this year, what we did is, that's the extra one, is we taught you about the friction force. Now, the first one is a static friction and a kinetic friction force. Now, we know friction force is indicated by a small f. But now we're going to talk about the static friction coefficient or the kinetic friction coefficient. Now, here I say friction coefficients usually have values smaller than 1. So remember, if you have to work that out, it's going to be 0.23 or 0.1 or so. Both static and kinetic friction coefficient are dependent on the characteristics or the type of the two surfaces. Now, what I want you to remember here is that the friction coefficient will never change. Say, for instance, the applied force change or the normal force change or whatever there was a change, and they say, what effect does it has on the coefficient, the μs or the μk? You say it will have no effect. Okay, because they try to ask you that and then you say no effect. The friction coefficient will also not have a unit. Now, the reason for that is, and I just want to show you something here. When we look at, let's say, the μk, the friction coefficient, kinetic friction coefficient, we get it alone on one side, it means that I have a friction force divided by a normal force, which is equals to μk. Now, the unit is newtons over newtons. No, because both of them are forces. So it means that it doesn't have a unit. Okay. So the reason that you're going to give when they say, why doesn't it have a unit or does it have a unit? Then you say, no, why not? Because it is a relationship between two forces. It is not, or it's a ratio between two forces. It is not it does not have a unit because of this. It's the ratio between two forces. Okay, the μk can be or will always be smaller than 1. And what we need to know, no unit, and it cannot change if any other forces change. The MK only or the MS only depends on the type of material that they use. So say, for instance, they say the slope was initially made out of wood and now they change it to glass, then the MK or the MS can change. Otherwise, it will always stay the same. Okay, just remember that. They ask that in testing exams to just try to see if you know that. Okay, now what I tried to do here is I summed up a few situations that you will get in forces. The first situation is where we have only an object. So let's make that go-kart a block. Only an object. There's an applied force. Can you see it's a rough surface? So there will be a friction force. And that is the only forces, external forces. And then, of course, we will have a gravitation force and a normal force. Now, if they ask us to draw the free body diagram for this situation, this is the easiest situation. A free body diagram will always be from a dot, and the forces will always have a line with an arrow mark. If you don't put in the arrow mark, you will not get a mark for your force. So the first force is always downwards, which is the gravitation force or the weight. So you can use it as a W or as the gravitation force. The next force is the normal force. Now, the normal force is the force that the surface area applies on this object. It's normally or always the same as the weight. Okay, you will see another situation where it's going to change a bit. Then we're going to have applied force, so that's F applied, and then we have a friction force. Now, the main thing that you need to remember about a free body diagram is to write out the forces. So when I do it, I will make a key next to it and write down N is for normal force, capital letter F is for applied force, or you can just say normal. So I'm just going to write it out. This is applied force. This is the weight or the gravitation force. So I'm going to write gravitation force. And then this is the friction force. Okay, so that the marker can see, you know what type of forces it is. Okay, now, very important to remember is that you must draw the free body diagram from a dot and you must show the arrow marks. Otherwise, they're not going to mark it right. Okay. Now, in each situation that you will see in this lesson, we're going to have a different way to work out the normal force. In this case, you will see that the normal force, which is this one, the only other force that is vertical is the weight. So in magnitude, the normal force is going to be equal to the weight. But in direction, it's going to be in the opposite direction. Okay. So when I work out the normal force, I'm going to say F normal, or just a capital letter N. Let's use a capital letter N for this one. So I'm going to say the normal force equals to the weight of the object. Now, how do we work out weight? Or Fg equals to M times G. Nah. Okay, so the weight is M times G. In this case, the mass of this object, and this is what I said, the object is 30 kilogram, and then G will always be 9,8. Okay, so when we work out the normal force, remember this is not actually about the sum, it's just to give you the different situations that you can expect when we do this. So 30 times 9,8 gives us 294 newtons. And the normal force, of course, is the force that is going upwards. You could have used F normal equals to Fg equals to Mg. Those are also fine to use. Okay, that's to work out the normal force. Now they give us the friction coefficient and they give us the applied force, but now they ask us to work out the friction force. Now, the moment when they give you the friction coefficient or so, the main thing that you need to remember is that you have to use this formula. And this formula is going to be on your information sheet. Okay. So rather use just me, that just the U, although this object is moving, so we can use me K for the moving of the object, and then F normal, so the normal force. So on the information sheet, it will look like this, or they will say F equals to me K, and then F normal, as you see it like that. Okay, so capital letter N is the same as the normal force. So when I have the normal force, what I just worked out, and I have the friction coefficient, I can just use that. And can you see the friction coefficient is smaller than 1? So it's 0.23 times 294, and 0.23 times 294 gives me an answer of 67.62 newtons. Okay, so it's just situation 1 where all the forces are either parallel with a surface area or horizontal with a surface area. The next one is the net force that we want to work out. Now, when we start to work with the net force, we must always show that we are working with Newton's second law. Now, when we look at Newton's second law, we're going to say F net equals to m times a. Now, I put this one first because if I write that one, then you can receive a mark if you fill in the rest. Okay, because sometimes in the second step, you tend to forget a force or something like that, and then still you can get a mark for F net equals to m times a. Now, when I look at this one, I say F net equals to m times a. They want us to work out F net, so I'm going to say F net equals. And now you must remember, and I'm going to talk about the front force minus the back force. That's how I'm going to talk about these forces. Now, when you look at your free body diagram, you know that these children are pushing this go-kart to the right. Can you see that in that picture that we have it? So the front will be this side. That's the front of the force. It's the front, it's in the direction which it is going. The back of the force will be behind the arrow in which direction it's going to go. So in this case, we're going to say the front force in this case is the applied force because the object is moving in that direction. And the back force is the friction force. So I'm going to say F net equals to the applied force. So F applied, I can indicate it by just the capital letter F. And then I can say plus minus friction. They accept it if you put immediately minus friction because the friction is working against the direction which the object is moving. So therefore it has a negative sign. So it's a front force minus the back force. Now when I substitute it in the question I said the applied force is 200 newtons. So we have the applied force and we just worked out the friction force which was 67.62. And then when we minus this 2, we're going to get an answer of 132.38 newtons. And then this one will go to the right. So I'm going to say, because friction is a vector, I'm going to say the force is, the net force is going to go to the right. It's the force that's going to let this go-kart go in a certain direction. Okay, now this was a simple one. This was where all the forces are either horizontal or parallel. The next situation that we're going to look at is, for instance, when a guy is pushing a lawnmower or where a person is pushing a trolley or something like that. Can you see my applied force is now downwards on this lawnmower? Can you see that? So my applied force have an angle now. All right. Now, when I look at this, I remember that the applied force is still 200 newtons. The mass of the object is still 30 kilograms. And the friction coefficient or the kinetic friction coefficient, because this object is moving, is still 0.23. When I draw the free body diagram now from a dot, I'm going to have the weight or the gravitation force. I have the normal force, okay, This is what I have. Then I have applied force, but my applied force is not horizontal. My applied force have an angle like that one. Okay. And I have a friction, but the friction is still going to be, because that's also, let's just put this in, that's also the definition for a friction force. The friction force is always parallel to the surface area, and it opposes the direction which the object is moving. Okay. Now, when I look at this, remember, you're going to write it out. This is your normal force. This is your applied force. This is the weight or the gravitation force. And then, of course, this is the friction force. Okay. Make sure that you have your arrow marks and that all the forces are going away from the dot. Okay. Now the normal force. And now when we work out the normal force, remember the previous one, we only had two vertical forces, a normal force and a weight. So for this one, it was easy to say. I'm going to say that the normal force is equal to the weight of the object. But now we have some of a problem, because we have a normal force that goes upwards, as you can see there. Then we have a weight, but I can divide the applied force into two components. Okay, so I have a Fx, which is the x component. No, some of you can't see the yellow. I have a Fx, which is the x component, and I have a Fy, which is the y component of the force. So when I look at all the vertical forces now, I'm going to have a normal force. I have the weight or the gravitation force, as well as the y component. And can you see the y component is downwards? So when I work out the normal force, again, remember this object stays on the ground. It's not going to float above the ground or sink into the ground. Now, so it means that all the forces that is at the top, the normal force, must be equal to all the forces that is pointing downwards. Okay. So in this case, we're going to do the following. We're going to say the normal force equals to, and now it's going to be the weight of the object plus the y component of the applied force. Okay, so don't forget about the y component of the applied force. Now we already worked out the weight. The weight is m times g. And to work out the y component, and this is not on the information sheet, so you really need to know how to work out the y component. So for the y component, it is what we did yesterday. We're going to use F sine theta. That's the y component. Can you see that? So F sine theta is the y component. Now when I substitute in, I have the mass, which is 30 times 9,8. The applied force is 200. And then I have sine, and the angle that it makes with the horizontal is 20 degrees. Okay. So when I do that with my calculator, you are supposed to get an answer of 362,4 and write the 0 newtons there. Remember, the paper says in the instruction that you have to round off to a minimum of 2 decimal places. So if you only have 1 decimal place, the marker can decide to mark it wrong. So even if it's a 0, just put it in, because it indicates that you know what is 2 decimal places. Okay. Now that's the normal force. Where's my book? Okay, so that's what we get for the normal force. Sorry, it was my book that pressed against the board there. Okay, then the next one is the friction force that they want to work out. Now, because we have the friction coefficient and we just work out the normal force, the friction force, we're going to do the following. We're going to say, right, friction equals to F normal. The friction coefficient is 0,23. times the normal force is 362,40. When I times that, I get the friction force in this case, and it's going to be 83,35 newtons. And in this case, if I give a direction, because a force has a magnitude, the direction will be to the left, because this object, the picture shows that the object is going to the right. When we work out the net force, remember we start with F net equals to M times A to show that we are working with Newton's second law. Okay. They want the net force, and now we're going to say equals to. And remember, at the first one I said it's equal to the front force minus the back force. Object is moving in that direction. So the front force is not going to be the applied force as you see it there. The front force must be the x component of the applied force. So for this one, we're going to say Fx plus minus friction. And now we're going to substitute in. What can we substitute? The x component of the applied force is going to be F cos theta. And that's what we did yesterday. F cos theta. Okay, let me just write neat here. All right. So it's F cos theta. Right. Minus friction. So when I substitute in, the applied force is 200 cos, and the angle is 20, minus the friction force that you just worked out, which is 83,35. And then the answer that we get for this one is going to be, the net force answer is 104,59 newtons to the right. Okay, so that would be the answer. All right, so now the moment when I have a flat surface, but the angle applied on the object, or the force applied on the object is with an angle, I have to remember I'm going to work with the x and the y component of the applied force. Don't forget that. Okay. The next one that we're going to look at is this one. So now instead of pushing down on this wagon or pushing down on the trolley or something like that, we're going to pull this certain object. Okay. Now when I look at the free body diagram, I'm going to have the weight, the normal force, I have an applied force, and I have a friction force. Okay, you write it out. If applied, normal, gravitation, and friction. Okay, all of them. Right. Normal force. Now let's quickly look at the normal force. Normal force equals to. And now we have two components. We have the x component of the applied force, and we have the y component. Now can you see the y component of the applied force is now upwards? All right. So now for this one, to work out the normal force, we're going to say it's the weight, and now we're going to say minus the y component. Okay, if I go back to the previous situation where we go down, can you see the y component word downwards in the same direction as the weight? So what did we do? We add the two. But now the moment when the situation is like that, the y component is upwards and the weight is downwards. So now we're going to minus the two from each other. So the weight we know is mg minus the y component is f sine theta, as you can see it there. So for this one, the weight we already worked out. It is that 30 times 9,8, which is 294. And then this one is the applied force, 200 sine 20. And then when we get an answer for the normal force, your answer should be 225,596 newtons. Okay, that is then your normal force. Now let's quickly compare the normal force of the previous situation with the normal force now. Now the previous situation, the normal force were 362,4. Can you see that? And now the normal force is 225,59. So it means that the normal force decreased. Okay, just keep that in mind. The normal force now decreased. The next one, we're going to work out the friction force. So friction equals to K because we have a friction coefficient times the normal force, which is Fn, or just a capital letter N. The friction coefficient is 0,23 and the normal force is 225,596. When we times this, you are going to get an answer of 51,89 newtons. Okay, and that would be to the left. Now, what I'm going to tell you now is important to remember. Can you see the friction force here is 51,89. And if I go back to the first or the second situation that I have, the friction force is 82,35. Now, what they do in a test or exam is they give you these two examples. The one with a guy pushing a trolley and the other one with a guy pulling the object. So it's a applied force downwards or applied force upwards. And then they say, how will the friction change? What is the change and why does the friction change between the two? Now, when I'm pulling an object like this one, the friction is lower. And the reason for that is because the normal force is smaller. Okay. So actually what is happening is when I'm pulling this crate, I'm actually lifting the crate. I'm applying a force upwards. So what am I doing? I'm decreasing the friction force. This is what I'm doing. Okay. Yes. Is there a question? Okay. If you want to ask a question at any time, you can just speak. Okay. Right. So in this case, when there's a force like this, when I'm pulling an object, it means I have the Y component of the applied force that is actually lifting this object from the ground. So it's decreasing the friction force. Okay. But if I'm pushing the object, I'm pushing it into the ground. So the Y component is downward. So I'm increasing the friction. So next time when you have to move a very heavy object, next time when you have to lift or move a very heavy object, okay, just remember that it's easier to pull the object than to try to push the object. Okay, right. So that's the difference between the two. The last situation, okay, and then F net. Let's quickly look at F net again. So F net, remember, we start with F net equals to M times A. Now, because I want F net, I'm going to say the front force, in this case again is the Fx, the X component, plus minus the friction force. How do we work out the X component? It is F cos theta minus friction. So when I substitute in there, it's 200, again 200 cos 20, and the friction force is then going to be 51,89. So can you see your F net is also increasing when the Y component is going upwards. So the answer is 136,05 newtons, and that would be to the right, as you can see it there. Okay, that is to the right. Okay. All right. The next situation is situation 4. Now we have a slope. And be careful for this one. because they always tend to forget one certain force when you are busy with the object that is going on a slope. Now, still I said, for each situation, we have applied force of 200 newtons. The mass of the object is 30 kilogram, and the kinetic friction coefficient is still 0.23. Now, when I look at this and I have to draw the free body diagram, I think it's always easier to just use a pencil and draw a very light pencil line that you can see your slope. Remember, the person who's marking your paper mustn't think it's a force actually that you try to put in there. Okay, so when I'm going to do this, my object, the crate, is this dot. What do I have? I have the weight. So there's the weight or the gravitation force. I have a normal force, and the definition for normal force is always that a normal force is perpendicular to the surface area. Now, this object goes on a slope. So when you look at this situation here, the normal force is perpendicular to the surface area, which is a 90-degree triangle, as you can see it there. All right. Now, the next force that we have, this guy is applying a force on this object. So there I have F applied. And then they talk about Fg K, which is a friction force. Okay, so that would be all the forces. But what you need to remember, yes, I'm going to keep this there. What you need to remember, if I have this object, that would be the weight. This is the normal force. Here I have the applied force, and there I have the friction force. And this is the slope that they are talking about there. Oh, I took you up. Okay. And this is the slope that we are talking about here. Sorry, where? Okay. Right. That would be the slope that we are talking about there. It means that this weight can be divided. Okay. This weight can be divided into two components. It can be divided into a FG perpendicular and a FG parallel component. Okay. And this, when we want to work out the FG perpendicular or the FG parallel, we're going to remember that now the formula is mg cos theta. So you mustn't get confused between the formula that we use for fx and fy and the formula that we use for fg perpendicular and fg parallel. So let me just write this one there. So I'm going to say fg parallel equals to mg sine theta. Okay. These two equations that you see here is not on the information sheet. So you must remember that. So even though the object is going up the slope or down the slope, gravitation will always try to pull an object to the center of the earth. So in this case, if I put a ball on the slope, what's going to happen with the ball? It's going to start to roll down the slope. Now, there's a force that is making that ball to go down the slope, and that force is then the gravitation force. Okay, we can't say the force is Fg parallel because that's a component of the gravitation force. So what does gravitation do? It makes sure that the object wants to go down the slope. So therefore, when we work with this, we must never forget about Fg parallel, the component of the force. Now you have a choice when you draw the free body diagram. Either you can draw the free body diagram as I did on the previous page. I will show it just now to you again. Or you can say, I have a normal force, F normal, or just a capital letter N. I have an applied force. I have a friction force. But now you're going to divide your weight or the gravitation force into FG perpendicular, and then a second force, which is FG parallel. But these two, the FG perpendicular and the FG parallel, will be considered as the gravitation force. So either the one where we have the gravitation force or the two components of the force. Not a mixture between the two, as you can see it here. If you do that, you're going to lose that mark. So either this one you're going to draw, or on the previous page, as I showed you, the one where I just show the weight and not the components of the weight. Okay. Right, so that's a free body diagram. Now, when we work out the normal force, and I'm going back to where I just showed you there, can you see the magnitude of the normal force is going to be equal in magnitude to the component of the gravitation force? Can you see that? So these two are going to be equal. So what I have to remember is that FG perpendicular, which is mg cos theta, is equal to the normal force. Okay, so this is how we're going to work out the normal force. So when I go back and I want to work out the normal force, I'm going to say normal force equals to FG perpendicular. What is the formula for FG perpendicular? It's going to be mg cos theta. And this you need to know, it's not on the information sheet. Okay. Which is then the mass of this object is 30 times 9,8 cos, and the slope is 20. Okay. And then when I work this out, I'm going to get an answer of 276.27 newtons. Okay. Right, so that's the answer. The next one that I'm looking at is the friction force that we need to work out. Same applies to this. So we can say friction equals to mk F normal, or just a capital letter N. Mk, we said it's still 0,23 times the normal force, which is 276,27. So when I times this 2, I'm going to get an answer of 63,54 newtons. That's a friction force. And then if I give the direction, I would say down this slope. Down the slope. Okay, that is the direction of the friction force. Okay, the next one is F net. Again, we start with F net equals to M times A. So then we can say F net equals 2. And again, we take the front force minus the back force. The object goes in that direction. So the front force is the applied force. Okay. Then the back force is friction, because there's friction. But it's here where you forget about FG parallel, because that's the force that is making sure that the object rolls down a slope. So I'm going to say plus minus FG parallel, as you can see it there. Okay. So now I'm going to substitute in. The applied force is 200 minus the friction force we worked out is 63,54. And then how do we work out FG parallel? We work out FG parallel by using mg sine theta. You must know that. And don't forget about FG parallel. So when I substitute it in, I'm going to say 200 minus 63,54, and then minus 30 is the mass, times 9,8 sine 20. And when we work this out, we get at the end the net force as 35,91 newtons. 35,91 newtons, as you can see it there. Okay, so when I have a slope, remember, then it changed. Then with a slope, I must remember I have FG perpendicular, which is going to be mg cos theta, and I have FG parallel, which is mg sine theta. Okay, that's for a slope. When I don't have the slope, if it's just a flat surface, I must remember about the x and the y component that we're going to use. Right. For the next one, let's quickly look at the next one. What I did, yes, I just put on the theory about Newton's first law. Now let's look at Newton's first law. Newton's first law actually says that every object will remain in a state of rest or continue moving with a constant velocity. Yes.
I would like to answer. I would like to question to make a question.
Okay. Yes, you can. You can ask a question.
Yeah, I would like to know whether a friction force is always negative or either positive or negative.
A friction force, if you work it out, will always oppose the direction which the object is moving. So if the object is moving to the one direction, the friction force will be in the negative direction. So when you substitute a friction force, it will always be negative because it is opposing the direction which the object is moving. And say, for instance, you get a negative answer. It means that the object is not going up the slope, it's actually going in the direction of the friction force. So yes, friction will always be negative. Okay. Okay. Right. Now, when we look at this one, Newton's first law, remember, in science, you must go and study the definitions, make sure that you know all the laws. Newton's first, second, third law, Newton's gravitation law, because that's the definitions that they're going to ask. Okay, so remember that. So the first one is Newton's first law. Now, the first law, they say it's actually object will move with a constant velocity, or it will stay in a state of rest unless external force works on it. So that is, say, for instance, I'm in a car, I'm not wearing my seat belt. Then this is going to happen with me. I am going to go on. My body wants to go on in that direction, in that certain direction. Unless I put on my safety belt, then it's an external force that works on it. Or I'm riding in a bus, the bus is pulling away. What is happening to your body? You fall backwards. And that is because of inertia that you go backwards. Why? Because the body wants to keep on standing still while the bus is going forward. So Newton's first law is also known as the law of inertia. Remember that. Okay, so that's Newton's first law. Newton's second law is the sums that we did. Newton's second law proved F net equals to m times a. Okay, and that's why we start with F net equals to m times a when we do a sum. It's just to prove we know we are using Newton's second law in this case. So when we use that law, we are going to work out the sums. So Newton's second law, that's the law that we need to know. When a net force acts, yes.
Ma'am,
Yes,
before
you
you
can
go
talk.
forward,
Sorry?
unmute. Unmute. There's a question that says, why does the body of a person, if he or she doesn't have a certain safety belt, why does he or she
keeps on moving
has
forward.
the same speed of which the car has moved?
Okay, it's because of Newton's first law. Because this object, the person or the object, will keep on moving with that velocity as the car were moving. Okay, unless the external force works on it. So if you are in a car, you're not wearing your safety belt, you're going to go through the windscreen with that velocity. Now remember, we are working in a closed system. So in this case, let's say if there were no wind resistance or anything like that, you are going to go with the same velocity. But now there's other objects or situations that plays a role that makes it do that you are not going to travel as fast. And we know mass is one of the things. A little child will go with a greater velocity than a big guy. Do you understand that? So mass plays a role and so on. So it's not going to go with the same velocity at which the car is moving because it depends on the mass. But because of Newton's second law, the object will keep on moving with that velocity unless an external force works on it. So in that question, I will say, according to Newton's second law, and then I will quote Newton's second law, and you will get your marks. Okay. Right. Now, definition, Newton's second law, the definition is important to remember. Remember, this is a longer definition, and therefore you need to know that this is the definition that they like to ask the most of all the Newton's laws. Now, the main thing that we must remember here when we look at the second law is that force and acceleration are directly proportional to each other. Okay. Now, when I talk about directly proportional, it means the greater the force, the faster the object will go, and that's a directly proportional equation. Okay, so force and acceleration are directly proportional to each other. Okay, so let's think of an example that we can use there. If I'm going in, let's say, a car with a 3-liter engine, it's a very big engine, it can put out a lot of force trying to let that car go out, faster. Then the car will accelerate faster than one with a 1300 engines. Now, I don't know anything about engines, so some of you are going to tell me, yes, but some cars have a turbo and I don't anything like that. But what you need to remember is the greater the force, the greater the acceleration. So if I have a cupboard here and I push the cupboard with a greater force, the faster the cupboard will move. Okay, right. Now when we look at the next situation is mass and acceleration. Okay, now of course, mass and acceleration is inverted proportional. Inverted proportional means 1 over A. Can you see that? Now, inverted proportional means if the one increases, the other one is going to decrease. Now, no offense to anyone, but if a small under or just if you have a fat person and a thin person and they have to run against each other, let's say 100 meter, I promise you the thin person is going to win. So the one with the least mass. Okay. So the mass is inverted proportional to acceleration. Okay. The greater the truck, the smaller the acceleration. The smaller the car, the mass of the car, the greater the acceleration. And when we talk about inverted proportional, it's actually indicated by a half hyperbole. You know what a hyperbole is. So directly proportional, the graph is a straight line through the origin. Okay, that's directly proportional. And inverted proportional, the graph look like this, as you can see it there on the board. Okay. The last law that we're going to talk about is Newton's third law, and that is applicable in our everyday situation. Newton's third law actually says, if object A or person A applies a force on object A will apply force on object B with the same magnitude, just in the opposite direction. Now, if you go and Google that, now you will see for every action there is a reaction, and that's how it works. Now, for every action there is a reaction. What we need to remember about Newton's third law is that the force is applied on two different objects. The guy is applying a force on the wall. The wall is applying the same force on the guy, just in the opposite direction. And that is how a rocket goes up in the air. The gases of the rocket applies a force on the ground, and the ground applies the same force in the opposite direction. So therefore, it's going to go upwards. Okay. According to Newton, the wall will exert a force on the person's hand that is equal in magnitude, but acts in the opposite direction. Okay, so that's Newton's third law. You must be able to use a situation and apply it to one of the laws. They like to ask that in a multiple choice question sometimes. Okay, so that's the laws. All right, it's a lot of theory, so let's quickly, I have a few minutes left, so I'm going to skip this before we go to Newton's gravitation law, and let's look at a previous grade 11 paper that I have here. Now, question 1, they say, in the diagram below, a 1 kilogram mass is on a horizontal surface connected to a 2 kilogram mass with a light rope that hangs over a frictionless pulley. The coefficient of kinetic friction between the 1 kilogram mass and the surface is 0.14. So this is μk. Okay. Then they say, write down Newton's second law. All of the sums I told you is according to Newton's second law. Okay. Then the next one, they say, determine the magnitude of number 1, the kinetic friction on the 1 kilogram mass piece. So they want us to work out the friction force. Now, what did I show you? Friction equals to μk and then times the normal force. Now, and when I look at this object, now, and I quickly draw myself a free body diagram for the 1 kilogram block. I have the gravitation force or the weight, the normal force. I have a tension force in the rope, and they talk about a friction coefficient, so there's a friction force. Okay, so to get the friction force, I have the μk, which is 0.13, and I have to work out the normal force. Now, because all the forces is on one line, what can I do? I can just say that the normal force is equal to the weight, which is the same as m times g, as you can see it there. So it's going to be 0.13 times the mass is 1 times 9.8. So when I times this, I'm going to get a friction force. And the friction force is going to be, the answer that we get is, I just want to get my answer here. That's question there. It's going to be here. That's better. Answer is 1.27 newtons. And because I just asked for the friction force, we have to say in which direction. And in this case, it is going to be to the left. Please don't leave out the direction, because if you leave out the direction, the answer is wrong. Okay. So remember to show the direction as well as the magnitude to get all your marks. The next question that they ask is the acceleration of the 1 kilogram mass piece. Okay, now they want us to work out the acceleration. All right, now let's quickly look at this. For the 1 kilogram block, this is going to be, just for myself, the 3 body diagrams. So I have the weight, normal force, applied force, friction force. Okay. When I want to work out acceleration, I can use F net equals to m times a. So I start with that, showing I'm working with Newton's second law. But because I want acceleration, I'm going to say m times a equals 2. And remember, this object is going to the right. So I'm going to say the front force minus the back force. The front force is the applied force, and then plus minus the friction force. Can you see? It's opposing the direction which the object is going. So now I want the acceleration. Oh, and then there's another force. Okay, let's just go back. Okay, so I have the tension. So let's just change that applied force to tension force. That will be better. Okay, I was looking for tension. So let's make that a capital letter T. All right, so it is going to be F net equals to the tension force minus the friction force. The mass is 1. I don't have the acceleration. I don't have the tension force. But I just worked out the friction force on the previous page, and the friction force was 1,27. So I'm going to substitute in 1,27. The moment when you get at this stage and you see you have two unknowns, can you see you have a T and you have an acceleration? Then you go to the next block and you go and check what does the next block give us. So the next block is the 2 kilogram block that's going to have a tension force and a gravitation force, because this block is just hanging there. So the 2 kilogram block, if I draw the free body diagram, it has a weight or the gravitation force and a tension force. Because it's not on a surface area, it does not have a normal force. So don't make a mistake and put in there a normal force, because this block is hanging in the air. There's no surface that is applied on this block. Okay. So I'm going to do the same for this one. I'm going to say F net equals to M times A. So I say M times A equals, now remember this 1 kilogram block is going to the right and this one is going to go downwards. So therefore I'm going to have the weight plus minus the tension, as you can see it there. Mass is 2, I don't know A. Okay, I have the weight because weight is M times G, so it's 2 times 9,8, and then I want tension. Can you see that? So now I can, let's just do this, equals to, what is 2 times 9,8? Is 19,6 minus tension. But I know it's one rope, it's a frictionless pulley that is that this rope is going over a frictionless pulley. So I know that the tension in both are the same. And because the tension for that, it's one rope, I'm going to try to get tension alone. So for this one, I'm going to say A plus 1,27 equals to tension. And on this side, I'm going to say tension equals to 19,6 minus 2A. And what can I do now? I can say, but I know tension equals to tension. Nah, it's the same thing. So A plus 1,27 equals to 19,6 minus 2A. And now I get the acceleration on the one side, the unknown, and then I have 19,6 minus the 1,27. So then I have 3A equals to the 19,6 minus the 1,27. So I got an acceleration of 6,11 meters per second square. And because they want the acceleration is also a vector quantity. So I must give the direction, and that would be to the right, as you can see it there. Okay. Right, everybody. So I am done with this question that you have here. So let's just go there. So A, I am done.
Hello, ma'am.
Yes.
Yeah, I have a question.
Okay.
So what's the direction of the acceleration for the whole system in the previous question?
In this question, to the right
Yes.
and downwards. You will say to the
Okay,
right and
so
down.
it's going
But the
to
question,
the right and down.
yes, but read the question. So please just check here. Where's the question now? Let me just go back.
If they ask me for the whole system, what do I say?
Then for the whole system, you're going to say right and downwards, but they ask the acceleration of the 1 kilogram block. Now, so then
Okay,
you
thank
say
you very
to
much,
the
ma'am.
right. Are you sharp? Okay.
Yes.
Anything
Thank
else?
you, ma'am. No, ma'am.
Okay. Okay, I will see you tomorrow. Remember, tomorrow it's a bit earlier, 9 o'clock. Okay, we are going on with this question. We're going to finish it before we start with Newton's gravitational law. So I'm going to break it up a bit. Okay, still going to do the slope and everything here, and then we will go back to Newton's gravitational law. I will see you tomorrow. Take care. Stay safe. Bye.